Thanks a lot to the organizers for giving me the opportunity to speak here. It's great to be back in Madrid and to see all of you. I'll be talking about applications of flops. The goal of the work is to flop curves in Calabi threefolds in order to explore the Kähler moduli space. This work is based on, the talk is based on a collection of works, 2 in progress, 2 already complete. Let me particularly highlight, see if I can get the pointer, apologize. I'm going to particularly highlight this forthcoming work with Naomi Gendler, Ben Heidenreich, Jakob Moritz, the sort of machinery that I'll be talking about today. Okay, so suppose X is a Calabi threefold and K of X is its Kähler cone pictured here. Now, sometimes it can happen that on a codimension 1 wall of the Kähler cone, some curve C in the threefold shrinks. And yet one can smoothly continue to some new phase, X prime, that's adjacent to the phase X. This can occur finitely many times or infinitely many times, depending on the example. And the key point is that some curves can be flopped and others cannot. Now, many phenomena of interest, for example, vacua, can only be found in some phases or might only be apparent in particular phases. And so if we want to explore the complement of the swampland, we need to traverse many phases. In particular, if one wants to try to prove a no-go result, then in principle, one needs to navigate through all possible phases and check the claimed no-go in all of them. So these are a collection of motivations for exploring the entirety of the moduli space. Here, I'm talking about the entirety of the Kähler moduli space in type 2 compactifications. Now, a brief remark, if X is actually a hypersurface in a toric variety, then many flops are easily evident from the toric description. And I want to stress that's not what this talk is about. We're not just going to look at the flops that are easy to find from the toric parent space. We're going to try to find all the flops. So the task is determine which curves can be flopped. Once we figured out which curves can be flopped, we can flop all around and explore the whole moduli space and try and characterize the physics all across it. Okay, so the plan of the talk, first, how do we find flops? And then, as promised in the title, applications. I'll give 2 applications. First, I'll briefly mention how one can test the weak gravity conjecture. This is work in progress. And then I'll describe how one can use flops to desingularize divisors and count fermion zero nodes. Okay, so what is a flop? So suppose X plus and X minus are Calabi threefolds. A flop's a birational map, from one to the other, that's an isomorphism away from some codimension 2 subvariety C. Now, a simple flop is a flop for which the singular locus, the locus away from which the map is an isomorphism, is actually just a smooth T1. Kawamata's theorem tells us that all birational maps between Calabi threefolds are compositions of simple flops. So that's a piece of motivation for trying to understand flops. Then we can explore the whole space of birationally equivalent Calabi threefolds. Now, back to the simple case that we'll not primarily be relying on, but is nice to picture. If X is a hypersurface in a toric variety, triangulation T to another one, change of triangulation is called the bistubble flip, and the curve C, pictured here, changes to some curve C prime. So this is a toric description of a flop. But even though such flops are numerous and easy to find, not all flops of this are of this sort. Okay, so we want to figure out which curves can be flopped. So what can happen at a wall of the Kähler cone? One of the following occurs. Possibility 1, one or more curves shrink, but no divisors shrink, and the threefold itself does not shrink. Possibility 2, a divisor shrinks to a curve of genus G. Possibility 3, a divisor shrinks all the way to a point. And possibility 4, the whole threefold shrinks. What we'd like to do is identify examples of case 1, because it's in case 1, a flop, in which the prepotential can be smoothly continued. In cases 2 and 3, one sees a rich range of interesting phenomena, and this talk is not about characterizing those phenomena. We want to find all different phases in which that are connected by transitions in which one or more curves shrink. And then once we reach transitions of type 2, 3, or even more so 4, we're just going to stop. So we're going to consider a maximal extension via transitions through walls of type 1, stopping at walls of type 2, 3, and 4. The fully extended Kähler cone, the maximally extended Kähler cone in this process is called the extended Kähler cone. So we're trying to find the extended Kähler. So how do we identify these kinds of walls? Well, your first thought might be, wait a minute, I see that in 2 and 3, a divisor shrinks, and in 4, the whole thing shrinks. So maybe I can just exclude cases 2 and 3 and assure myself that I'm in case 1 by checking that no divisors shrink. That's not as easy as it sounds because you have to know what all the effective divisors are. If you have a list of all the effective divisors, it's very easy to check whether any of them shrinks on a wall. But in general, the list of effective divisors on the Calabi-Yau threefold is not available. Computing it in general is a relatively open problem. Although, now this is a parenthetical remark because today's talk is not mostly about computing effective divisors. I should stress that a side consequence of the methodology I'll be describing today is a new way of getting the effective cone. The idea for how this can work was laid out in these works. Way of getting the effective divisors from the extended Kähler cone. Okay, but the summary here is that this naive idea is not necessarily going to work, so let's try something different. Okay, and so the core idea of our work is to use Gopakumar-Vafa invariance to set up a criterion for forms. So suppose Q is some curve class in H2, and T is a vector of Kähler parameters, then the Mori cone of the threefold is the set of all curve classes that have positive volume for all T inside the Kähler cone. In other words, it's the dual cone to the Kähler cone. And the prepotential contains a generally infinite series of contributions whose numerical integer prefactors are the GV invariants of curves, and then these are times some trilogarithm of exponentials in the moduli. I'd briefly remind you that if you're more familiar with Gromov-Witten invariants, the Gopakumar-Vafa invariants are just related by a resummation. GW times exponential, all summed, is GV times trilogarithm, all summed. Now, we're going to use GV invariants to sort curves into 2 types, 2 kinds of curves. First kind, I will call a curve nilpotent if there exists some number k max such that for all k greater than k max, the GV invariant of kq is equal to 0. Okay, so let me repeat that. I pick a curve class q, and I look at all multiples kq, and I ask, is it ever the case that the series of GV invariants terminates and I only get zeros for k bigger than some k max? If that's the case, I have a finite series of GV invariants along a ray in the Mori cone, and I call such a curve and such a ray nilpotent. The other possibility is a potent ray or a potent curve. Along a potent curve, there are infinitely many non-zero GV invariants. So this is the key distinction. So let's look at an example. A simple example of a nilpotent curve is a curve where the GV invariant of C is 1 and the GV invariant of twice C, 3 times C, et cetera, is all 0. Here's an example from a Calabi-Yau threefold hypersurface with 113 Kähler moduli. The GV invariants of C, 2C, et cetera, are 3, minus 6, dot, dot, dot. And then you can go up to 100 and it just keeps growing and growing. It's just exponentially growing. Let me stress, we don't have exact results in this work. So when I say that I find an example of a curve that's potent, well, we think it's potent because we got up to degree 100 and it kept growing. And I've never seen volume. The whole infinite series of instanton contributions to the prepotential is going to have to be resummed. The simplest thing that you can think about happening, could happen this way, is that as a potent curve shrinks to zero volume, an infinite number of BPS states go to zero mass. The BPS states with charges that are multiples of the charge of the curve. More complicated things could happen, but in general, one who's faced with infinitely many instantons being resummed. Now, that doesn't mean you can't possibly make sense of it, but it's certainly not just a flop. Okay, so potent curves are just not flop curves. Some highly non-trivial resummation would be required to pass through a wall where a potent curve shrinks. How about nilpotent curves? Well, if a nilpotent curve shrinks to zero volume, it's, well, first of all, certainly true that there are finitely many instantons of charges that are multiples of Q that need to be continued past the flop, or the would-be flop. And so naively, you might think that every nilpotent curve is a flop curve, and we have our perfect distinction. Potent curves are not flop curves, and nilpotent ones are. That's not quite right. What if, as I shrink some nilpotent curve to zero volume, infinitely many instantons of charges that are actually not multiples of Q also have to be continued? This happens, actually. So let's go through that and explain why. So we're going to define a cone, the infinity cone. This is the subcone of the Mori cone. The infinity cone is defined to be the cone generated by potent curves. So I find all the potent curves and make a cone out of them. That's some subcone inside the Mori cone. Now, a nilpotent curve could be strictly outside the infinity cone, or it could be somewhere in the closure of the infinity cone, either strictly inside the infinity cone or in the boundary. So here's some pictures. The lattice shown is H2 of XC for some fictitious example X, the Calabi-Yau threefold. And the dots are sites with non-zero GV invariance. So the red dot is a nilpotent curve, and all the purple dots are potent curves. The shaded purple region is the infinity cone in both examples. Now, in the example on the left, I have a nilpotent curve that's strictly outside the infinity cone. And in the right, well, the infinity cone is, the closure of the infinity cone is the first quadrant. So this nilpotent curve is actually inside it. But note that the points here along the axis are not populated by non-zero GV invariance. So the x-axis really is a potent ray, and the red dot really is a nilpotent curve. Okay, so this is the strictly outside case, and this is the boundary case. So let's use this to sort out flops. Okay, our main claim is a GV flop criterion. We claim C is a flop curve, and if and only if C is strictly outside the infinity cone. Okay, and here's a proof. I don't want to imply that it's a very rigorous proof, but the idea is as follows. If C is strictly outside the infinity cone, then as I go to a wall of the Kähler cone where C shrinks, no potent curves are shrinking. Because no potent curves are shrinking, I only have to continue finitely many trilogarithms through the would-be flop. And one can then check that it really is a flop. Okay, well, if the curve is strictly inside the infinity cone, then one or more potent curves shrink on the wall where C shrinks. And so infinitely many instantons must be resummed, and this thing isn't the flop. Okay, boundary case. What if the curve in question is on the boundary of the infinity cone? Well, when any curve shrinks, terms in the prepotential that differ by multiples of that curve class end up being summed up in a way that I'll show quite explicitly in a moment. If C is in the boundary of the infinity cone, these sums end up being infinite. There's an infinite degeneracy. There are infinitely many terms that differ by multiples of the curve that's shrinking, and one can't simply continue that. So let's see this in an example, as it sounds a little bit obscure. Okay, so here's the toy example. The nilpotent curve class has charges 1, 0. It's pictured there in red. And the prepotential will look like some sum of GV invariants where n and m are summed over this first quadrant. GV of n comma m, e to the minus, well, n times the Kähler modulus tx plus m times the Kähler modulus ty. And for big enough tx and ty, this is an absolutely convergent sum and everything's good. What we want to know is what happens if we go to the wall of this cone. Now, the curve C is in the boundary of the infinity cone, and it shrinks when tx equals 0. And what happens when tx equals 0? I can rewrite this sum as a sum over m's and then sum over n's exponential of m times ty. And the point is that for every m greater than 0, namely for this row and for this row and for this row, one is summing all the way along the row, and all but finitely many things along each row are non-zero integers. So each of these sums is an infinite sum of non-zero integers. So they certainly don't converge. And the whole thing is not convergent. And hence, this isn't a flop. Some highly non-trivial resummation would be required to make it through this wall. Okay, and so in conclusion, not only in the case here of a curve, so only in the case where a curve is strictly outside the infinity cone can we actually continue. Now, what's this good for? This criterion is only usable if you can compute enough these genus 0 GV invariants to actually find the infinity cone and apply the criterion, right? And we can do that. For X, a hypersurface and a toric variety, we can compute GV invariants, even at the largest case, H11 equals 4921. This is some forthcoming work. It's done in CY tools. And the method is an extension of a long-established approach due to Hausenauer, Clem, Theisen, and Yao from the mid-90s. Basic idea is you compute the fundamental period, use the intersection data of the mirror, and have to use a little bit of cleverness in terms of not wasting one's time computing GV invariants of curves that are going to be non-effective anyway. So there are a collection of rather technical advances embedded in our approach, but that's not something I'll get into now. I'm happy to talk about it afterward if anyone's curious. Bottom line, we can compute enough GV invariants to make use of this criterion. And so now we actually have an easy way of identifying all the flops. So again, a picture, here's the Mori cone in some example. And here in the interior, for example, is the infinity cone. And then there's a lot of nilpotent curves around it. A typical picture that one sees at large H11 is there are many possible flops, many nilpotent curves, and the infinity cone is often quite narrow. So what does the extended Kähler cone look like then? By computing GVs and detecting flops, we can map out the whole thing. So what we have here are some toric phases that are easy to find from the parent toric description, a collection of non-toric, but still geometric phases. The flop between two toric phases can often be understood easily as a bistellar flip. And the flops from blue to red or from red to red are not bistellar flips. They're more complicated or more subtle flops, but one can still understand them. And the connection to effective divisors, the divisors that shrink at the boundary of the extended Kähler cone are effective divisors. So this is the maximal extension of the Kähler moduli space via flops. Okay, so now let's turn to applications. First application is the weak gravity conjecture. So the Tower and sublattice weak gravity conjecture make highly non-trivial predictions for BPS states. They also make predictions for non-BPS states, but let's think about BPS ones for a minute. So let's imagine we're doing M theory Fabia threefold. Then the GV invariants are counting, well, our BPS indices. And when a GV invariant for some curve class Q is non-zero, that tells us there's at least one BPS state of electric charge. So can we use GV invariants to test strong forms of the weak gravity conjecture? By the way, I should say that everything that I'm saying on this slide was laid out in very thorough and serious work by Elim, Heidenreich, and Redelius from last year that we're building on. So this approach, trying to use GV invariants to test strong forms of WGC, it could exclude, but it can't prove a weak gravity conjecture for two reasons. First is, there's a possibility of cancellations. The GV invariant is an index after all. So if a GV invariant is zero, that doesn't mean necessarily that there's no BPS state. But if a GV invariant is non-zero, then there is at least one BPS state. And secondly, an approach that's testing BPS predictions or predictions for BPS states doesn't get any information about the non-BPS directions in charge space. So conjecture that holds for all BPS states might fail for non-BPS states. Nevertheless, we can still learn a lot, and let's look where we can look. This is something but one can really compute. Now, what does this have to do with flops, you may be saying? Well, the BPS states come from M2 branes wrapping effective curves, and in each phase of the Calabi-Yau, each chamber of the effective Kähler cone, different curves may be effective. And so by flopping around, one has a different set of states that one might want to test. Now, where does weak gravity make predictions? So again, I'm quoting directly the work of Elim, Heidenreich, Redelius. The BPS sublattice weak gravity conjecture can be stated as follows. There exists an integer k greater than or equal to 1, such that for every direction, so for every charge q, in a direction in which the BPS and black hole extremality bounds coincide, there's necessarily a BPS particle of charge kq. So what's the point here? The sublattice WGC is I think familiar to everybody, but the key point is in a direction in which the BPS and black hole extremality bounds coincide. So the weak gravity conjecture makes useful predictions, easily testable predictions for BPS states if black holes, extremal black holes is what weak gravity is about, and BPS states coincide. So one has to know in which directions in the charge space is that in fact true. That's what this work did. The directions in which BPS and black hole extremality bounds coincide corresponds to the dual of the effective cone of movable curves. Now, that allowed these authors to rewrite the sublattice weak gravity conjecture as a purely geometric statement. Any CY3, there exists an integer k such that for any non-trivial class in the intersection of H2 with the dual of the effective cone, there's necessarily a holomorphic curve in class Q. And now we're in business. Now we can actually test something because the Tower and sublattice weak gravity conjecture necessarily predict that the dual of the effective cone is in the infinity cone. And that's why I was talking about the infinity cone. So here's an algorithm to test weak gravity. You start with a Calabi threefold, compute GV invariance, find the infinity cone, flop all the flop curves, maximally extend the Kähler cone, construct the extended Kähler cone and the effective cone, check all the charges in the dual of the effective cone up to some cutoff degree. Okay, and so we've done this. We've carried out this test in thousands of Calabi threefold hypersurfaces. It's work in progress, so I won't show you a lot of pretty pictures. Let me just show you one and stress that we find no violations of the lattice weak gravity conjecture. So here's one very preliminary picture produced yesterday for case H11 equals 4, 631 different polytopes, 6,579 phases, and every one of them obeys lattice, not sublattice. So what's being shown here? Polytope ID, which is just sort of an arbitrary ID, and in blue are the number of toric phases. Those are the ones we could have easily gotten from triangulations. And then in orange are the non-toric phases. These are the ones that needed the new methods that we deployed here. And you might have thought a priori that maybe the violations will only occur in the non-toric phases or something like that. Okay, so one just really needs to check everywhere in the moduli space. And for these examples, we've checked the entire extended Kähler cone up to some reasonable degree, and we can't find any violations so far. Okay, so in the last couple minutes, let me say one quick thing about another use of flops. Maybe we can talk about it afterward, which is about singular divisors. So in type 2b flux magnifications, Euclidean D3 branes make crucial contributions to the potential for the Kähler moduli, and one would like to know which divisors support Euclidean free branes. Now, it's well known that if D is rigid and orientifold even, namely it obeys these conditions, and is smooth, then the number of fermion zero modes is 2, and Euclidean D3 branes wrapping that divisor D contribute a term like this with a not identically zero Pfaffi. This is the famous sufficient condition, also known as the rigidity condition due to Witten in 1996. The problem is effective divisors of a Calabi threefold are quite generically not smooth. Here's an intuitive picture. Suppose D1 through DH11 is a basis of H4 corresponding to some local coordinates. Then a divisor like D1 plus D2 corresponds to the vanishing locus of X1 times X2. And that thing has a normal crossing singularity where two components is not smooth. However, it's maybe not the worst kind of singularity. Sometimes these kinds of things can be removed, sometimes not. What we're going to see is that the prevalence of a slightly worse type of singularity, which we call a star crossing singularity, is actually linked to the prevalence of flops. So the picture of the slightly worse kind is shown here. Instead of a layer of two things on top, here one has three things crossing at the singular point. This is from work this spring. So can we count zero modes in this case? Well, with flops we can. So consider a divisor that has singularities at codimension 1 along some locus C. If C is a rational curve, in that case we call the singularity a star crossing. And around C, some number of local components meet. If the number of local components meeting is just 2, that's a normal crossing. That's the example I already showed. But in general, the number could be more than 2 components. So here's 3 components. And here's how you can think about it. These 3 components are all meeting. The dashed line is a rational curve that you could sort of imagine collapsing to make the singular. Now, what does this have to do with flops? Well, suppose C is a flop curve that locally looks like the resolved conifold, and D is a smooth divisor that intersects the curve in 2 or more points. Then when you go through the flop, it glues together K components of the divisor. It stitches them together. So imagine this dashed line here is a flop curve. And when you go through and flop it, the different pieces get glued together along the shrunken curve. So these sorts of singularities are simply made when one passes through flops. But I've already shown you in the previous pictures, there are flops all over the place. There are tons of different phases. So if you take a configuration that has a bunch of smooth divisors, and you start flopping curves and going to other phases, you're going to stitch together the divisors upon themselves and make them singular. That makes the zero mode counting problem seem hard because you're faced with singular divisors. But we can count fermion zero modes in this case by running the process in reverse. Given some D that has star crossing singularities along a curve C, we just carry out flops to undo the gluing, thanks, along the curve. So we start with something D that's singular. I go through a bunch of flops to make it smooth. And the nice thing is the superpotential can be continued through the flops because it's holomorphic. So if I find a configuration where once I have smoothed it, it obeys the standard rigidity condition, then by the continuation, there's a contribution in the smooth configuration and hence one even in the original singular configuration. So more generally, the normalization of a divisor is defined by separating the components that meet over some locus. And so in my last minute, let me say we can define well, a birational invariant, which is the Hodge vector of the normalization of the divisor. And if there exists a phase where D is smooth, then we apply Witten's sufficient criterion in the smooth phase and find a contribution. But crucially, the normalization of a smooth divisor is the divisor itself. And so the Hodge vector of the smooth thing also matches the Hodge vector of the normalization. And that means that this Hagel, that's the name of this rune here, Hagel of D Hagel of D equals 1, 0, 0 is actually the sufficient condition for a Euclidean D3 brane contribution in cases where one can smooth by a series of flops. So brief warning here, our claim is proved in cases in which a series of flops does unwind the singularity, but it's logically possible there might be cases where there isn't such a flop series. In that case, what we're proposing here is the natural conjecture, but we can't actually give a direct use of it. Okay, so let me conclude. We use the computation of GV invariants to explore moduli space. Our core claim was a flop criterion that C is a flop curve if and only if it's strictly outside the infinity cone. And we use this for two applications. One of them is testing predictions of weak gravity in BPS directions, in which case we found no violations of lattice weak gravity. That was a bit of a surprise to us. And then the second application was using flops of this sort to desingularize divisors and hence count fermion zero modes. Thanks a lot.
Questions? Miguel? Oh, sorry, Federico.
Hey, Liam, thanks for the very nice talk. So I wanted to ask the examples in which you found lattice, are they, did you ever look at Calabi-Yau with non-trivial fundamental group?
Yeah, that's a great question. We definitely would suspect that that's the place to find a possible sublattice. And yeah, we haven't done that yet. Okay. So that's one aspect of the work in progress is cleaning up a systematic look at hypersurfaces up to some degree and up to some H11. And the other part of the work is making sure that we try our hardest to find examples where there's a non-trivial fundamental group. So maybe we can find a sublattice. Yeah. Although frankly, when at least I'm not speaking for my collaborators here, but when we started, I sort of thought we would find violations in at least some small percentage of the cases just right out of the Kreutzer-Skarka box. And so far we have.
Okay, thanks.
Thanks, Liam, for the super nice talk. So I was thinking, every time you have a conifold transition, you also have a flop because you can go in the resolve phase two different ways. So if you claim that you have all the flops, maybe you have also the conical transitions as a subset of them. Did you think about that?
Yeah, so we didn't attempt to enumerate conical transitions, but I agree with your statement. Yeah. Yeah, we should talk afterward if you think there's an interesting way of making use of a sort of categorization. I mean, effectively, you're saying, you know, the data of where all the conical transitions can possibly be is contained in the data of the extended Kähler cone,
Yes,
right?
yes.
And so, yeah, our game is generating the extended Kähler cone, and so indeed it supplies that capability. So it'd be fun to see what.
Yeah, systematic way for finding conical transitions in Kruserskerk is an open problem, for example.
Thanks.
Yeah, thank you, Liam, for this a very nice talk. So one question is about this singularization that you are proposing if you have these various components. So physically, this means that there are open strings probably from one component to the other. And if you do the transition, so these can pair up, right, and become massive. So, but in the phase that you are in the moment, I would think that, so you have vector-like, what we call usually vector-like zero modes. And only by, again, giving a VEF to the Kähler modulus to move into the other phase, you actually get a contribution to the prepotential. So I would say, if this is the correct interpretation, that in the phase that you are in, where you have a singular divisor, that there's no contribution to the prepotential.
Let's see. So I'm talking at this stage of the talk, I was talking about contributions to the superpotential. So I mean, an n=1 model with trying to count to two zero modes. But on your point, so these intersections are along rational curves. So without flux there, there's nothing chiral living there. And so the only zero modes one is getting are from the components themselves, not from the locus of intersection. So if we were to try, now one could try, we didn't do it in the paper, one could try to understand star crossing type generalization of star crossing singularities where two components of a divisor meet along a curve of genus G. Then for sure there would be some complicated issue with open string modes at the intersection. But if it's a P1, I don't see that there's a possibility.
Okay, so okay, I understand. So you're saying these extra zero modes that might be there, they are not coming from the intersection of the components. They're not localized on the singularity.
That's right. So the extra zero modes really, so this Hegel of D has this nice additive property. So if D is actually a sum of distinct components, then Hegel of D is just the sum of Hegel of the DIs. And so, you know, if you can, in a case where you literally have D1 plus D2, then you can just take those two pieces apart and you get the pure sum of those contributions without any novel piece from the locus of interaction. So that's how the formula works, and it squares with the claim that, you know, there's nothing living on P1.
Okay, thank you very much.
Thanks a lot.
Well, I don't see any more questions, so let's thank